the top, switch to the pointer, or the enolates under basic conditions. And one might be asking, well, why do we bring up these different weak and strong bases? We're going to see that in a minute. So we had a variety of different bases to form the enolates. We then used halogenation as a good example to first introduce the mechanism of an enolate or enol reaction as a kind of a baseline mechanism. And we saw that we could take bromine in the presence of acid and this aldehyde in the top here, and we would alpha halogenate this compound, or introduce a halogen at the alpha position. And we highlighted the importance of stereochemistry and that we're generating this sp2 hybridized enol intermediate. Now, one thing you'll also notice is when we did the halogenation reaction here, under acidic conditions, we only added one bromine. We didn't keep on adding bromines. This is an important difference between the acid and base conditions here, and that as we add a bromine here now, we are actually would make the proton more acidic. We would also destabilize the formation of the enol intermediate. Now, if the ketone is not symmetric, this was what we're going to get to a little bit more. We saw that we could generate under acidic conditions. We're still under acidic conditions, potentially two different products, but we saw a major and a minor product. And this comes down to stability of the enol intermediate. And we talked about slow, not stop, right? Slow steps in the reaction. And this would be an excellent place for a free energy diagram, actually, coming back to it. So we'll skip over HVZ. And then we talked about basic conditions here now, where we can then pull the proton off on the left here, generate our enolate, halogenate. Now we've generated a more acidic proton, which we're going to take off again, halogenate, and then the haloform reaction is doing this over and over again until we make that potentially good leaving group. Okay, so now let's think a little bit more about some other reactions, two reactions in particular with these enolates. This is known as direct alkylation. This is very useful because we're actually forming a new carbon-carbon bond. So let's take this methyl cyclohexanone again as our baseline compound. And notice now we're going to react it with this propyl iodide in each case. And if we react this with sodium methoxide as our base at 25 degrees, it looks like the propyl group is added to the more substituted carbon. And you will end up generating stereoisomers in this case, in each of these, but we're ignoring that for simplicity. However, if we use our stronger base, and it's LDA, and also a lower temperature, now it looks like the alkyl group is added to the less substituted carbon. So this is great because we can actually form a new carbon-carbon bond. We were just introducing this propyl group, but we can actually also decide, do we want the propyl group being added to the more substituted, the top case, or the less substituted carbon. And it looks like the choice of base is the key determinant, and the temperature. So in terms of a mechanism, actually there's really nothing new for our mechanism, is let's take the top case. So let's just draw this in a generic sense. Let's take off the proton on the top, on the right, and why don't we write, it's going to write base to start with. We generate this enolate. Or we could take off the proton on the left side. I'm going to avoid all of those colors, I'm not sure if that was helpful or not. So we'll use, say, base again, where we could form this enolate. Now, in each of these cases, we just like in the previous case where we were looking at more or less substituted, this top enolate is the more substituted alkene, which would be the more stable alkene, or the thermodynamic product. Whereas this bottom enolate is the less substituted, less stable. But the key thing is that this proton over here that's just dangling out on the left side, it's not hindered like this proton that's next to this methyl group. So it's going to actually be easier to remove that. So this will end up being the kinetic product. So the way to think about this is that in top case, generating our enolate, the rate limiting step is the deprotonation to generate the enolate. So sodium methoxide is our weaker base, and this step is in equilibrium to generate the enolate. So sometimes it'll pick up this proton, sometimes it'll pick up the easier proton, but it's forming a less substituted, less stable product. And so that'll just go back and forth in equilibrium. So we'll write the enolate intermediate like this. So in the end, the major intermediate that's going to be formed will be the more stable species. I'll keep scrolling up. Whereas our base, kind of crooked, like LDA, which let's draw here, these big isopropyl groups, very strong base, sterically hindered. So let's just write this hydrogen as kind of being small. So this big base is going to be energetically unfavorable for it to take this more sterically hindered proton off. So it's predominantly just going to go ahead and rip off this other proton over here that's more accessible, even though that forms the less stable alkene. And this is generally not reversible, so it's just going to end up forming this enolate. On top of this, what we can do is lower the temperature to the minus 78 degrees, so that's going to disfavor the reaction agent going backwards even more. Whereas to help promote equilibrium, we'll keep this around close to room temperature. Now, in each case, what we can do is have this enolate act as our nucleophile in an SN2 reaction. It goes back to the classic SN2. We have a good leaving group. It's not sterically hindered. So we'll end up reforming our carbonyl group, and I'll write it same. How did I do it up here? Same way. Like this. Same thing down here. It's kind of a long arrow, but parallel the top. SN2 reaction. Forming our product. I'm not sure if this is due to shaking or the angle I'm holding the thing at. So, all right, so the key thing is, this is our thermodynamic product. And this is our kinetic product. And to reiterate that, I think this is we will draw a free energy profile here, just to highlight that first step. So here's our free energy, here's our reaction coordinate. And what we want to think about is forming our enolates. So starting from our alkene, and we have the two protons that we can take off. I'm not sure if colors here might help. Let's use I think we had green, maybe it's purple before. So forming or taking off this more hindered proton, let's do this one first. This is energetically unfavorable, but it's going to form something that will be more stable than if we took off the other proton. So this is going to end up having, high barrier, but forming, say, something like this. The relative energies are a little off here, but are more substituted, more stable alkene. Now, the big bulky base that can pull off this less hindered proton over here on the left, that's going to require less energy. So there'll be a lower activation energy barrier, but it's going to end up forming something that is not as stable. And so this is going to be our kinetic product. And the green one is our thermodynamic product. So to help bring everything together, this is the rate limiting step of the reaction. This is the slow step. What we want to do is, for the green case, is we're going to have a base. It'll be in equilibrium. So sometimes it'll form the less stable product, but there's enough energy around so it can go back over that barrier and try again. And then there'll be a population of molecules that will have enough energy to overcome this activation energy barrier, but it takes time. It's slower, overall for the rate limiting step because there's fewer that can surmount this barrier. But when they do, they form the more substituted, more stable intermediate, and then they'll go on to react in the SN2 step. The kinetic product, we have a low temperature, so we're trying to reduce the number of molecules that can actually cross this high energy barrier. Instead, they'll just cross the lower energy barrier. The purple one, even though the intermediate is less stable, it's at a low temperature, so they're less likely to be able to go back. And then they'll just go forward in forming the more stable, the less stable, less substituted product in the end. So the base and the temperature plays a role. Big, bulky base just to rip this proton off to carry the reaction forward and prohibit or minimize removing this proton. Low temperature to prevent the molecules from going back and forth in equilibrium. And the less substituted base here, the F oxide weaker base, to favor equilibrium conditions, so that even though there's a higher barrier, we end up forming the more stable intermediates. So it goes back to reactions that we've seen before, like with 1,2,1,4 addition and stuff like that. Okay, and then underneath all of this is a very useful synthetic reaction. We're forming a carbon-carbon bond with the enolate. We're using the enolate as our carbon nucleophile. And the actual alkylation reaction here is an SN2 reaction. Okay, any other comments or questions about